Hi there, Mr. Sutton here, bringing you the AB Calculus 611 homework solutions on accumulation and rate out free response questions. On this problem, we have people entering a line for an escalator at a rate modeled by this function below, where from 0 to 300 seconds, that's what t is measured in here, we've got this weird function, and, well, after 300 seconds, I guess no one wants to get on the escalator. So as people get on the escalator, they are exiting the line at a constant rate of 0.7 people per second. And we're starting with 20. So we have an initial value of 20. We have a rate in of this. And we have a rate out of 0.7. Given that setup, part A asks how many people enter the line for the escalator during the interval from 0 to 300. So we have the rate at which people are entering here. We just need to integrate that from 0 to 300 to get the number of people who get on in that time interval. So I'm going to write the integral from 0 to 300 of r of t dt, and let's do that on the calculator. So to help me out on this problem, I've entered this crazy function here in my y1. Quitting out of that now, let me do math 9, and then 0 to 300, so I'm making my integral here. And then I'm going to call up the function I just entered, so alpha trace y1, and then dx, and that comes out to, oh, look at that, exactly 270. Usually you do these problems and you get like a fraction of a person, but this is 270 whole people. For this next part of the problem, they tell us that during the time interval from 0 to 300, there are always people in line for the escalator. How many people are in line at time 300? So I'm going to define a function, which I'll call p of t, which will represent the number of people in line. I don't know exactly how to express this just yet, but I know its derivative, p prime of t, the rate of change of people in line. That's going to be the rate in, represented by r of t, minus the rate out, represented by this 0.7 that are actually exiting the line every second. So I'm going to write p prime of t equals r of t minus 0.7. And now I can use this p prime forever after in this problem. Okay, so to figure out how many people are in line at time 300, I need to take the initial number of people, so I can say p of 300 equals 20 plus the integral from 0 to 300 of this p prime function. I'm integrating the rate of change of people in line, and that gives me the total change in people in line. So I'll need the calculator for this. And on the calculator, I've defined y2 as essentially y1, or r of t, minus 0.7. I mean, it's a small difference, but now I don't have to keep plugging that in. And then let me get out of here, and let me do 20 plus the integral, so math 9, 0 to 300. And then I'll do alpha trace y2 to pull up that p prime function, and then dx. And so that's going to be 80 people. There are 80 people at the end of 300 seconds. For part C, this is kind of interesting. For time greater than 300, what's the first time there are no people in line for the escalator? So here's the situation. For the first 300 seconds, people are getting on the escalator according to this function up here. After 300 seconds, nobody is getting on the escalator, but we still have 0.7 persons per second getting off the escalator. So we're starting with 80 people at time 300, and from that we're going to subtract something with this 0.7 in it. So we're doing minus 0.7, and I just have to multiply this by how many seconds have elapsed since we hit 300. So I'm going to write negative 0.7 times t minus 300. So that way, for example, if I'm at the 303rd second, I'm really just multiplying this 0.7 by 3, and that's the number of people who have gotten off the escalator for that 3 seconds. Now, this is not an equation just yet. In order to solve for this time here, I need to actually set this equal to something. We want to know the first time there are no people in the line for the escalator. So I'm going to set this equal to 0, because that's what we want it to be. All right, so just a little bit of algebra here. Subtract 80 from both sides, then we can divide by negative 0.7, and finally add 300. So just rearranging things to isolate t. And you could actually stick seconds on the end of this and be done, or you can plug it in the calculator. So plugging all that in is going to give me 414.286, and that's going to be seconds. For this last part of the problem, they want to know between times 0 and 300, at what time is the number of people in line a minimum? And then to the nearest whole number, find the number of people in line at this time. All right, so for this, I'm trying to minimize the p of t function that I came up with in part B, and I'm going to need to find critical values for p prime of t. So I'm going to let p prime of t, which I defined earlier as r of t minus 0.7, I'm going to let that stuff equal 0. And let me solve this on my grapher now. So on my grapher, again, I have that p prime of t function in my y2, and I've got the equals enabled only for that. I don't want to graph the r function by itself. I just want this p prime graphed. What window should I use? Well, they asked about time 0 to 300, and that's a pretty big window, but we're going to have to graph that whole thing and then zoom 0 this thing, zoom fit, and just hope our calculator gives us something that is easy to look at. So here's our p prime of t function. It goes up, it goes down, and we see that we definitely have some critical values where this thing equals 0. Now, before we go ahead and find both critical values, we're looking to see where p is at a minimum. That means we only need to consider local mins when we're looking at these critical values. The only place where p prime is changing from negative to positive is this first spot right here. This other spot is a critical value, but it's going to be a local max, so there's no way it can be the minimum for the overall function. So let's do second trace 0, and we're just going to find this first one right here. So I'm going to enter 0 directly to get my left bound, so I don't have to move the spider so far. And then I'll move my spider to the right here, a little bit to the right of this, and press enter again, enter a third time, and we have our critical value at 33.0133. Now I'm immediately going to quit out of my graphing screen, and I'm going to store that value as alpha A, or alpha whatever you want, so I can pull it back whenever I need to. In fact, and this is the graph that I just looked this up on, in fact, I'm going to say that in order to only consider this critical value, I'm going to say that p prime changes negative to positive at t equals a equals that big number only. So I've done a few things with this sentence. I'm saying that, hey, there's a critical value here, and I'm considering only this critical value because this is my only local min. So this phrasing allows me to not even bother looking at this other critical value. And I'm also letting a represent that number so that I can use it in my work whenever I want now. All right, we've got our critical value. We've got two endpoints, 0 and 300. It's time to run the candidates test and see which one of these gives us the smallest number when we plug it into the p function. So let's start with p of 0, the left endpoint. Well, that's the number of people at time 0. That's 20. They gave us that. Great. How about p of a? Well, that's going to be my initial 20 people plus the integral from time 0 to time a of p prime of t dt. For that, I'll need the calculator. So here's how I entered this in the calculator. I had my 20, math 9 for my integral, 0 to a, where I stored that value I just got. And then y2 again, that's where I have my p prime stored on the calculator. Pressing enter, that comes out to 3.8 and some change. But these are people we're talking about. And they want us to figure out to the nearest whole number the min number of people. So I'm going to round this to 4. Can't have a fraction of a person. All right. So now we have one more to look at, p of 300, and as it happens, we already figured that out earlier, the number of people in line at 300 seconds. That was 80 from an earlier part in the problem, so we didn't actually even need to do any work beyond looking back at our past work. Now looking at all of these, it looks like our min occurs at a seconds where we have 4 people waiting in line. For this problem, our setup is that we have water being pumped into a tank modeled by this WT function. This is the rate at which water is being pumped in. And this is happening on 0 to 8 for time. And then water is removed at a rate modeled by R of t. And R is differentiable, decreasing, and selected values of this removal function are in this table. So we have a rate in, we have a rate out. And, of course, they're going to give us the initial value somewhere. Yep, there it is, 50,000 liters of water in the tank at time 0. So for our first problem, we just want to find the estimate for r prime of 2, and then show the work and indicate units of measure. Okay, so first of all, what are the units of measure going to be? Well, the r function itself is liters per hour, so this is the rate of change in liters per hour over time. So we're going to expect units of liters per hour, or liters per hour squared. So let's go ahead and find out what the number is. Since we're asking for an estimate for this instantaneous rate of change, and all we have to work with is this table, we're going to use the average rate of change of r over an interval that contains time 2. Probably the best interval would be 1 to 3, but you could actually use any interval that has a 2 somewhere in the middle. So I'm going to do the AROC from 1 to 3. This is going to be r of 3 minus r of 1 over 3 minus 1, which is to say 950 minus 1190 over 3 minus 1. And I'm going to use the calculator to simplify that. Although I actually don't even need to simplify it. I could just put liters per hour squared on the end and call it a day. But I like simplifying things because I'm not actually taking the AP test right this second. So here we go. I'm just going to plug this into my fancy fraction, alpha y equals n over d. And that comes out to negative 120. So again, that's negative 120 liters per hour squared. For part B, they want us to use a left Riemann sum with 4 subintervals using the table here to estimate the total amount of water removed for the first 8 hours. And then they want to know, is it an over or underestimate and why? All right, well, let's start with the Riemann sum. So I'm essentially taking the integral of the r function from 0 to 8, and I can now say that is approximately equal to the following. And I have to write approximately equals because, again, this is an approximation. I'm not getting the exact value. So they said left Riemann sum. So I'm going to do rectangles, base times height. We have first off a base of 1 times a height of 1340 because I'm using the left side of the rectangle, the left y value that I could make a rectangle out of. Next we have a base of 2 times a height of 1190 plus base of 3 times a height of 950. And finally base of 2 from 6 to 8 times the height of 740. And we could put units on the end and call it a day on this. The units are going to be liters because you are estimating the total amount of water removed. The amount of water is liters. But I'm just going to plug this in the calculator and see what the actual number is. So plugging all that in, I get 8,050, and again, that's going to be liters. So that's the first part of this problem. Next, they want to know if this is an over or underestimate of the total amount of water removed. So to figure this out, we have to look at the type of Riemann sum, which is a left Riemann sum, and we have to consider whether this is an increasing or decreasing function on the interval in question. So we see here they said this is decreasing on the interval from 0 to 8. I'm going to write that down. And you have to mention the interval here or you're not going to get full credit. So decreasing on the interval from 0 to 8. Therefore, because this is LRAM and decreasing, this is automatically going to be an overestimate. If your function's going down, your left rectangles that are touching the curve are always going to give you area that's above the curve. So I can say then that 8,050 is greater than the true value of this integral here, which is to say I have an overestimate. For part C, they want us to use our answer from part B, which again was 8,050, to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. So for this one, we have to consider 3 things. First off, we have the liters that were in the tank in the very beginning. So our total water is going to be 50,000 plus some things. So now we have to add the water that gets pumped in over 8 hours. The rate of pumping in is this W of t. So I need to add the integral of this W of t dt from 0 to 8. And then finally, I have to subtract the total water that we lost, which again was that 8,050 that we estimated in part B using this table. So let me plug this in the calculator. To help me with this, I'm going to put this W of t crazy function in my y1 for y equals. And then let me quit out of there. So I've got 50,000 plus the integral, so plus math 9, from 0 to 8 of, well, we just put that in y1, so alpha trace y1 dx, and then I'm going to subtract from all that the 8,050 that I got in part B, getting a grand total of, and they wanted this to the nearest liters, so 49,786. And again, that's liters. For this last part, they're asking for the interval 0 to 8, is there a time when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. So this is kind of a tricky one. You're going to have to take a little bit to think about this. But the idea, what they're really looking for here, is for you to come up with some expression that has W of t and R of t in it. If W of t and R of t are the same thing, if we put them together and they're the same thing, if we subtract them, it ought to give us a value of 0. So we're basically asking the question, are we guaranteed that W of t minus R of t is going to equal 0 somewhere on the interval from 0 to 8? So let's go ahead and set up the groundwork for this kind of proof. Since we're going to be using the intermediate value theorem, we need to establish that W of t minus R of t is continuous. So let me start by saying that W of t and R of t are individually continuous. We know this because W of t is just an exponential function. And in the exponential function, you have a polynomial, so there's nothing here that's going to break continuity. And then we have R of t, which, although they just gave us a table, they did tell us it was differentiable. Therefore, we know it is also continuous. So if these functions are individually continuous, that means that if I subtract them, W of t minus R of t must also be continuous. Subtraction is not going to affect continuity. All right, well, at this point, we're going to try to show that the output value of 0 is sandwiched between W minus R of some input on the table and W minus R of some other input on the table. So let me start by calculating W of 0 minus R of 0. I don't know what my magic interval is going to be that has a value of 0 sandwiched in it, but I'm going to start with the endpoints 0 and 8 because, well, why not? So let me plug this in the calculator. To do this on the calculator, I'm going to do alpha trace y1 of 0, parentheses 0, because that's where I stored my W of t function. And I'm going to subtract R of 0, which in the table they told us is 1340. So that comes out to 660. Okay, well, I'm really hoping that when I do W of 8 minus R of 8, I get some kind of negative number because we want 0 to be between this number and whatever I get here. So let me go ahead and try that out on the calculator. And I'm going to just note now, because my calculator is going to cover it, that R of 8 is 700. So going back to my calculator, I'm going to do, let's see, I'm just going to yank the input from before, and I'm going to replace 0 with 8 in my W function. And then this is going to be 700. Enter. That's negative 618.476. And 0 is clearly between these two numbers. Therefore, by the intermediate value theorem, we are guaranteed that W of t minus R of t must equal 0 somewhere on the interval from 0 to 8. But that doesn't quite answer the question, because they wanted to know, are we guaranteed that R and W equal each other, that the rate at which water is pumped in and the rate at which it's removed are the same. But we can just add R of t to the other side, and now we can guarantee by the same theorem that W of t equals R of t on the interval from 0 to 8. For this problem, we have a tree trunk with a circular cross-section at a certain height, and the radius of that cross-section, which we're calling R of t, grows at a rate modeled by dr over dt, given here. And this only applies between times 0 and 3. And at time 0, they're telling us our radius is 6, and the area is this a of t function that they're not going to tell us anything else about. They didn't tell us anything about R of t either, other than what it represents. So for part A, we want an expression with an integral for the radius R of t between time 0 and 3, and then we want to use that to find R of 3. All right, well, if I want the radius at any time, I need to take into account my starting radius, which was 6, and I'm going to have to add the integral of the rate of change of the radius, dr over dt, or r prime of t, from 0 to, well, whenever I want to find out for the time here. So I'm going to do an integral from 0 to t of, now before I put t in here, I have to have a different variable in my upper limit and inside the integral. My dummy variable can't match the limit variable here, because that's overusing the variable. So I'm going to write, instead of r prime of t dt, I'm going to write r prime of x dx. But we understand that that's really just this thing up here. All right, so now I'm going to find r of 3 using that. And to help myself do this, I'm going to put my r prime inside my calculator as y equals y1 right here. So now I can use it whenever I need to. Let me quit out of that now and actually enter this in my calculator for R3. So I'm going to have 6 plus the integral, so math 9, from 0 to, we said 3, because they want us to find R of 3, of, and now I'm going to do alpha trace y1 dx, and let's see what that comes out to. So that's going to be 6.611, and that is going to be in centimeters. For part B, they want us to find the rate at which our cross-sectional area, A of t, is increasing at 3 years with units of measure. So first we need to define A of t. That's going to be just pi r squared, because this is just a circle we're talking about. So in this case, it's going to be pi times r of t squared, because r is actually a function in this problem. And now if I want to find the rate at which our area is changing or increasing, then I need to take the derivative of this, a prime of t. Using my power rule, that's just going to be 2 pi times r of t, but r itself is a function, so I'm also going to have to multiply this by r prime of t. I'm going to have to use my chain rule on this one, inner function. Okay, so now I just have to plug 3 into all this. Now the beauty of this is r is already defined. We actually defined this in part A. So I don't need to really say what I'm doing, beyond using the calculator to find r of 3. In fact, we actually already found r of 3 on the last problem, so we could use that value again. R prime of 3. Well, we've defined r prime. It's up here, so we can just plug 3 into that as well without really showing a whole lot. So I'm going to do the rest of this problem on the calculator. So here I go on the calculator. I've got 2 pi times, now I want r of 3. Well, that's actually this value I just found, so I'm just going to arrow up, grab that, and put it right there. Times, now I want the derivative of r, which is actually already my y1 in my calculator. So I'm going to do alpha trace, pull up y1, and I'll just plug 3 into that. And let's see where the chips fall on this one. Oh, that was pretty quick. 8.858. And now we have to figure out the units on this. Since this is the rate at which the area is growing, that's going to be centimeters squared per year. For this last problem part, we want to evaluate integral from 0 to 3 of a prime of t dt, and then interpret the meaning of this integral in terms of cross-sectional area. All right, well, if I'm taking the integral of this thing, I'm just taking the antiderivative of a prime, which is just a. So we are evaluating that, a of t, from 0 to 3, which is just simply a of 3 minus a of 0. Now we have to actually get a number out of this. So this is where, if you haven't already, you're going to have to do something in the calculator to represent the a function. Now going back to the last problem, we have the a function listed here as pi times r of t squared. So that's probably the easiest way to do this, is just put this in our calculator. To make this happen, I'm going to first set up the function r in my y2. So that's going to be that initial value of 6 plus the integral, so math 9, from, we said 0 to, I need a variable now. I'll do 0 to x, and then that was just this function up here, y1. So alpha trace y1, and I'll just put dx here. Now, normally you shouldn't do this on paper, but your calculator doesn't really care if this variable and this variable match. It does something crazy with local variables and all of those sorts of fun programming tricks to make this work. So this is r right here. This is what we defined in part A. So now I need to just do another function where I'm doing pi times this stuff squared. So I'm going to do pi. That's not pi. Let's try again. Let's see. Second exponent button. There we go. Nope. All right, let's try one more time. And here we go. Pi. There we go. Now we've got y2, and we're going to square that. So alpha trace y2, square that. And now this y3 function is going to give me my area at any t value. Okay, so moving back to where we were, let's see here. There we are. We need to do a of 3 minus a of 0. So on the calculator then, let me quit out. That's going to look like alpha trace y3, parentheses 3, minus alpha trace y3, 0. And that's going to give us a total of 24.201. All right, let's figure out the units on this now. This is, let's see here, we're integrating the change in the area. So this is the total amount the area is changing. It's going to be in the same units as area. So this is going to be centimeters squared. Now, what does this actually mean? Well, as I said, this is the total change in area in centimeters squared from 0 to 3 years.